Hello class. So today's topic is similitude. From the name, you can kind of get the idea. It is actually the similitude actually uh, will tell you something about the similar magnitude. That's why it's similitude. So what does similitude actually mean? Suppose you have to calculate some forces for a ship or some boats in the water, or you want to calculate what will be the drag force around in like airplane or the car. So what you can do, doing the experiment on the actual size, you can actually make some model and you can do some testing in controlled environment, like you can control everything and then you can do the experimentation, and uh, you can actually use the results from that experimentation to the actual object using the similitude. Okay, so the similitude is a mathematical process of ensuring that the model used for an experimental study will correspond to the behavior of the prototype when the prototype is subjected to actual fluid flow. Okay, now we need to know what is prototype and what is the model. So uh, model is often used. Model is the one on which you will do the experimentation. It can be uh, bigger than the original object. It can be smaller than the original object, but on the object you do all the experimentation in a controlled environment. That is the model, and the prototype is the actual object for which the model is made. Now when you do all the experimentation on the model and you want to use that results to understand the behavior, fluid behavior for the prototype or the actual object, obviously you need to have some relationship, like there needs to be something like similar or similarities between the model or prototype. Otherwise you can't just replicate the results from the model to prototype. Just for an example, you can't replicate the result for uh, a circular pipe to a culvert in like culvert which has the rectangular opening or something, because they are not just the similar, like they don't show the similar characteristics. So if you want to replicate some results from the circular pipe to a culvert, that culvert has to, like that culvert must have the opening which is circular. Only that time you can actually replicate the result from the model to prototype. So what I'm trying to say is simply that there must be some similarities or some sort of ratios, or so that you can actually replicate the results from the model to the prototype. Now here are some examples you can see. So the first one is the wind tunnel. So inside any wind tunnel, you can actually test what will be the drag force around aeroplane wings, or what will be the drag force of air around any car or something like that. So wind tunnel, usually it's a big setup where you can do all the testings, and you can also uh, set the wind turbines to offshore, just to see what is the wave loading on something, on any bridge pier or something like that. You can do that testing also. For this one, uh, this is the effect of wind on high-rise building. How can you do that? So this is some sort of small model on wind tunnel, and these are some models you can test, like what are the effects. Now all these three examples, they are showing that we are doing all the like experimentation on a small scale project, and we will replicate to that, to the actual object which is bigger than this model. But there can be some cases where you will do all the experimentation on a bigger model, and then you will use that for a smaller model, just like this one, like the flow of air through the blades of a turbine used for a dental drill. Itself is a small setup, but to understand better, usually that all the testing or all the experimentations they usually do that on a model which is much bigger than the actual one. Okay. So as I was seeing, there must be some sort of measure so that you can replicate the results from the model to the actual object. So there are three types of similitude we need to consider. The first one is the geometric similitude. That is actually the geometric similitude is you can get the idea that it's geometry, it's related to geometry. So it says that all of the model's linear dimension must be in the same proportion as those of the prototype, and all its angle must be same. So this one is kind of like similar triangle, like it's kind of, okay. So, and this is called the scale ratio, the linear proportion of the length of the model to the length of the prototype. Okay, M stands for model, P stands for prototype. And if the ratio is maintained for all dimensions, like length, width, height, then it follows that the area of the volume will be proportional as well. So the volume, obviously, it's M square, AP square, and the volume is Pm square cube, and just the area. And for volume, it's three-dimensional. That's why it's cube. Okay. So that is the geometric similitude. Now the kinematic similitude. Kinematic is it's related to the flow. So the primary dimension defining kinematic similitude are time and length, because V equals to L over T. So for example, some velocity similitude would be Vm over Vp. So I can write down this way. And if you do the rearrangement, you will get with this one. Now, the most important and the most useful one is the dynamic similitude. So dynamic, it's related to forces. So it says that all but one of the force ratios acting on the fluid particle in the model and the prototype must be equal. Okay. And the force ratio can be expressed as any type of force over the force inertia force here. Okay. And that any type force can be due to pressure, due to viscosity, due to gravity, surface tension, or elasticity. And if I remind you about one slide we discussed in dimensional analysis, so these are just dimensionless number related to the force. You can see for Reynolds number, it's inertia over viscous force. So for Froude number, inertia over gravitational. Euler's number, pressure force over inertia. And you can see for any type of numbers, we have the inertia force here. So if I go back to this sentence that the force ratio can be expressed as Vm over Vi, like F over Fi. So that simply tells you this F can be like inertia, gravity, surface tension, like anything, pressure over the inertia force. That means you should get either Reynolds number or Froude number or Euler's number, Weber number, Mach number, something like that. So that simply tells you for the model and for the prototype, either the Reynolds number or the Froude number or the Weber number, like one number should be equal. Now we need to select which number we should choose, but before doing that, let's make clear that what we are trying to say, that for model and prototype, the number, at least one dimensionless number should be same. Okay. Now, if we go to that summary table, there are some examples, and we can check which force is the dominant one, and based on that, we can select that. So one of the common thing is flow through pipes and ducts. Usually for that one, viscous is the important one, so we should use Reynolds number for pipe flow. Open channel, dam, spillway, wave action on structure, mostly about like it's about the gravity, and so for that one we will use the Froude number. So okay. And just like this one, you can find which number you need to use based on that, and after reading the problem statement, we need to decide which number we should use. Okay. After that, we should do two class examples. It's the class example 21 and 22. So let's start working on the class example 21. It says that the dam is to be built such that the estimated average flow over its crest. So this one is called crest, to be 1,000 meter cube per second. That's a huge amount of flow. Determine, because it's the dam flow, so determine the required flow over the crest of a model built to a scale of 125. So in this question, the actual flow was given, and you need to go, like you need to do back calculation to find what was the model, what was the flow they found when they did the testing on a model. And we know the scale ratio also, which is 1/25. Okay, so since this is dam and it's an open channel flow, we can go back to this table and we can see open channel dam spillway wave action on the structure. We need to calculate the Froude. We need to use the Froude number for the model and the prototype, and they should be same. Only that time we can say that the result can be replicated from the model to prototype. Okay, so the first, let's write down the first statement. Gravity force dominates. So use, okay, and let's write down all the given values. Okay, so we have a scale ratio, that is the first one. It says that determine the required flow over the crest of a model built to a scale. So model was built to a scale of 125. That means the model was 25 smaller than the original one. So LM over LP is 1/20. Okay. And we also know the Q for prototype QP, which is 3,000 millimeters per second. And we need to find what is the Q model. Okay. To make sure we know this one. Okay. So let's go to the next slide. So we need to set this way: Froude number for prototype equals to Froude number for model. Now, the Froude number expression is V G L. You can get that from the slide where I put all the dimensionless number expression. G L. Okay. Now, the equation is for V, but we don't have the V. So what we can do, we can actually express the V in terms of A. So that's what we will do. Q over A. Root over G on both sides. So we can cancel those. So that direction. So now it's Q P A P L P Q M M L M. Now, just a few minutes ago, we saw that for like similitude, you can actually say the area is what? The square of the length. So LP square, LP, M. Okay. So this one So now it's QP over LP cube, QM over LM cube. If I move to the next slide, QP over LP cube, QM LM cube. And since we are looking for QM, so I will keep QM on one side and everything else on the other side. Okay. So QP, since they both have like cube, I can simply write down that way. So QM equals to QP, and LM and LP, that was actually given here 1 over 25. So what we can do here, and class, I think I made a slight mistake. So for L, we had the root also. So everything is root. So instead of 3, it will be half and 2. So that is 5 over 2. So that should be 5 over 2. Okay. So we will not have cube, cube. It will be 5 over 2, 5 over 2. Okay, and if you do the calculation, you should get 0.960. So on actual model, you got, sorry, actual object, you got 3000. And here, when you did the testing, you should get 0.96 meter cube per second. And that is the answer for this class example 21. So let's start class example 22. It says that a machine to be operated in oil having a kinematic viscosity of, so this one is actually mu here. If the viscous and gravity forces predominate during the flow, determine the required viscosity of the liquid used with the model. The model is built to a scale of 1 over 10. Now, notice this statement: if the viscous and the gravity forces are predominant during the flow. That means for gravity force, we already know that we need to use Froude number. For viscous, let's check the table for viscous, which force we need to use. For viscous, we need to use the Reynolds number. Okay, so that means we need to use the Reynolds number. Okay, so for this problem, for prototype and model, gravity and viscous forces, they like the Froude number for model and prototype will be same, and the Reynolds number for prototype and model will be same. Okay, so let's start with the given values. Then we will find what we need to calculate. Okay, okay. So the given values, the very first one is the viscosity, kinematic viscosity of the prototype, the actual one, which is 0.035 meters per second. And we also know the model is built to a scale. So that means L model over L prototype equals to 1 over 10. And you need to find the required viscosity of a liquid used with the model. Okay, so that's what we need to find here. What we will do, the solution since we know the Froude number and the Reynolds number will be same for prototype and the model. So let's start with the Froude number first. We know that. So Froude number for model for prototype and Reynolds number for model. Number for prototype. That should be the one. So I'll move to the next slide so that I can see everything while I will do the calculation. So Froude number for prototype, Froude number for model, and you know the expression. We just did one class example in this one, right? You can cancel GG and it will be so since we know LM over LP, I will try to express this one in terms of LM over LP. So how can I do that? I will move that LM this side. Okay. And that will give me okay. So that is equation 1. So Reynolds number prototype, Reynolds number model. And if you go back to that slide, you will see the expression for this one is L and the kinematic viscosity. V, L, and the kinematic viscosity. Okay. Now, what we can do, we can actually rearrange these equations such a way so that I can use some values from here. So here we have LMLP, we have VP, so we can do in any way. So since we have VM over VP in this case, so I will try to rearrange this equation, VM over VP. So it will be VM over VP, so LP over LM, and VM over VP, LP over LM, viscosity over, is that correct? So VM over VP, LP over LM, yes, that is correct. So we can use the VM over VP value from the equation 1, which is this one. Just make a note. Let me just say how did I find that? Okay. So I will just move to the next slide. What's the previous one? LM, viscosity and viscosity. Oops. So that one was just opposite. This one. Okay. So what we will do, since we are looking for viscosity of M, I will keep that on the same side and I will move everything on the other side. So this one, I'm just moving that one. Okay. So here you have 1.5. So that will be 3/2 viscosity up here. And I'm just moving here. So Pm equals to Lp/Lm is 1/10. We know that. 3/2. We also know the viscosity. And if you do the calculation, you should get 1.107 into 10 to the power 6 meters per second. So that is the answer for this question. And like the required viscosity of the liquid used with the model. So that was the viscosity for the model, and this was the viscosity for the actual project. Now here you can see in this problem both the fluid was liquid, but it can be air and liquid both, but that will not create any problem because you will use the individual viscosity, and that will solve the problem by itself. Okay, that's it. Thank you.